Hello, everyone. My name is Tom Paley, and I'm a PhD candidate at Indiana University. And today I'm presenting some work with my co-authors Victor Jose, Asa Paley, Ralph Keeney, and Mario Jurich. And I'll be talking about our decision model we developed for policymakers who might be considering how to invest in telescopes that can drastically accelerate our detection rates and cataloging of near-Earth objects, and how to make decisions that can potentially prevent asteroid or comet impacts here on Earth. So first I'll start with some background on near-Earth objects and their devastating potential. And here we have two examples of NEO impacts that are on different ends of the spectrum of damage to Earth. Now on the left is the so-called Tunguska event, which was in 1908 in this remote area in Russia, and an asteroid roughly 50 meters in diameter burned up in the atmosphere before it could reach the Earth's surface. And fortunately, the area was sparsely populated, but the shock wave from the explosion was strong enough to level almost 100 million trees. And to contextualize the amount of energy involved, it was roughly equal to 1,000 atomic bombs. And at 50 meters, this is what scientists consider the smallest NEO capable of reaching Earth's surface before disintegrating. And on the other hand, on the right, we have the 10-kilometer asteroid whose impact caused mass extinctions, wiping out 75% of all plant and animal species around the world. Obviously would have an unfathomable impact if anything like that were to happen today. So there's a continuous spectrum of NEO impacts between those two examples of impact events, but we can group them into four types here, and with a representative example or population-weighted prototypical object for each type. And these first two, the small and medium categories, would have localized effects, whereas NEOs in the large and very large category would have the potential to cause global effects no matter where they hit. And there's a wide range of objects out there, but scientists generally believe, so anything smaller than 50 meters, like the Tunguska event, would disintegrate before it reaches the Earth's surface. And this picture on the left is of the widely documented 20-meter asteroid over Chelyabinsk, Russia, which did disintegrate, but the shockwave after the explosion proved that NEOs of even this size can still cause damage to a lot of buildings nearby and cause injuries. But we'll focus on these four potential hazards. So how can we detect near-Earth objects? Well, simple answer, with a telescope. And by continuously scanning the sky and comparing images, telescopes can catalog NEOs, and we can then predict with a great deal of precision when there may be any close passes of a particular NEO many years in the future. And there's a network of existing smaller telescopes that is doing this now, but there is also a much more capable and very expensive land-based telescope under construction right now, the Vera Rubin LSST, which is near completion. A space-based NEO surveyor has also been proposed and has the potential to be built in the next few years. And both of these have the potential to drastically accelerate the rate of discovery of NEOs. Well, why is discovery important? Well, because we can do something about it. So if we know one will impact the Earth in the future, we can destroy or otherwise change its trajectory. And NASA had a test mission last fall on an asteroid that under our classification chart would be considered large, and it was a success. So they did this test mission called the DART mission, and successfully able to change its trajectory. And next I'd like to just mention a few stakeholders for this project. Some of them are going to be quite obvious, but first we'd like to mention the B612 Foundation, whose mission is to spread the word about this threat and to help develop tools and technologies that can help us expand our knowledge of the solar system and asteroid impacts. And B612 was able to put us in touch with one of our now co-authors, Mario, who's been instrumental in ensuring that our decision analysis, model development, and parameterization was up to speed with the latest astrophysics research. So we're very grateful to B612 for their support. Now, the U.S. Congress has also played a big role in guiding decision makings about NEO detection. So in the early 90s, they issued the first so-called Space Guard survey, which instructed NASA to find and catalog 90% of the estimated population of the largest NEOs out there. So the very large objects, those 1 kilometer or more in diameter. And they provided funding for nearly all of the early small land-based telescopes that ended up successfully meeting that goal. And then in 2005, they said, okay, well, let's move on to tracking 90% of objects 140 meters or more in diameter. But they're only about halfway done with that goal as of today. So potentially there may be a need for Congress to issue another mandate or increase funding for NASA to develop telescopes to help meet these goals. And obviously, who benefits from this? Well, potentially all of the human race and planet Earth. So you might think the decision to invest in telescopes is pretty straightforward, right? Well, just in the past 10 years, we've seen a lot of inconsistent decision-making by NASA administrators on this issue. And pretty soon after the meteor explosion in Russia in 2013, NASA was saying, essentially, don't worry, it doesn't make sense to spend a lot on these telescopes. It's unlikely to affect us. And then just 6 years later, we see NASA saying, well, we're on board to fund the most expensive telescope proposed, the space-based NEO Surveyor. And then earlier this year, we see NASA saying, well, actually, we don't have the funds right now, so we're putting this off. So clearly some inconsistent decision-making. And our goal with this paper is to say to NASA and Congress and any other policymakers around the world who might be considering this problem, well, let's approach this using some decision analysis methods and rigorously examine this decision. And the first step to doing our approach to this is identifying some different options that we have, and we'll call them alternatives. So we identify 4 different alternatives, and the first one of these we include for completeness, which is that we could end all telescope funding and basically hope for the best given our discoveries so far. Well, that would certainly be the cheapest option. Another option is just to stick with funding our existing telescopes, which are continuing to discover and track NEOs at a relatively modest rate. The next alternative, and here we see some substantial increases in cost, is to fund the Vera Rubin LSST, which will have the largest digital camera ever constructed. And finally, we can throw the kitchen sink at the problem and also fund the space-based NEO Surveyor mission. Now, based on the most recent population estimates for near-Earth objects and scientific literature estimating those discovery rates for these different telescopes, we can estimate the probabilities of finding NEOs of different sizes. And we show the estimates of these in that last column just for small NEOs as an example. So our next step is to develop a decision tree, and we look at, given these potential investments, what's the probability of detection of our different NEO threats over a 50-year planning horizon. So we also include mitigation and evacuation decisions if we do detect one of these objects on track to impact Earth, and there's some probability of success for these different missions. And we next identify the objectives that policymakers would have in selecting one of the investments. Now, the most obvious objective, immediately clear, is preventing the loss of life from such an impact. And that's our first, what we call, fundamental objective. There are also economic costs involved in this decision, both from a potential NEO impact and from the decision of the chosen strategy. And we also consider protecting non-human life, so minimizing the environmental damage that would come from some of these larger NEO impacts, in particular, those large enough to cause global effects and potentially extinguish different species. And finally, we will also want to consider the scientific contributions and technological benefits to society that would come along with these different telescopes we consider. Now, given these 6 different objectives, we will need to estimate a value trade-off for each one. And once we've done this for each objective, we'll have this multi-attribute utility function on the bottom here, which is essentially a weighted sum of each of our objectives given their value trade-offs. Now, for the last 2 objectives, calculating the utility associated with each of those potential telescopes is a bit more complicated, and for that we use constructed scales. And this lets us estimate those benefits so we can properly incorporate these more 2 tricky objectives into our multi-attribute utility function. And there are many, many parameters, as you might guess, that we use to calibrate this decision model. And these first ones are largely removed from the astrophysics literature. The VSL parameter, in particular, is an ethical dilemma for any policymaker. And here we rely on population-weighted estimates from some meta-analysis in public economics literature. And as we will discuss, our sensitivity analysis is particularly important for this parameter, as there's a wide range of VSLs that a policymaker may deem appropriate and is seen in practice. And this next set of parameters shows us, for each of these different NEO size categories, what are the probabilities of impacts, mitigation success, in addition to the economic and other cost parameters that we would need to calibrate our decision tree. And finally, we also needed to estimate, based on the most recent population and discovery estimates, how would each of our decision alternatives perform at discovering representative NEOs from each of our size categories. And as you imagine, the more we invest, the greater our discovery rates across all of these hazard types. So once we calibrated our model, we can examine the relative impacts that each of these NEO size categories has on a policymaker's utility. So here we show the probability of impact on a log scale on the vertical axis, and our prototypical small NEOs would have a negative effect on the utility that is overall relatively small. But as we examine larger and larger NEO categories, we can see that while the probability decreases exponentially, the expected effects on utility also exponentially increase, as you might expect. So the larger impacts obviously cause a lot more utility loss for the policymaker if there were an impact. And the red circle for each type just shows the fraction that remains undiscovered in that category. So next you can see that when we properly weight the expected damages by that percentage of undiscovered NEOs of each size, the greatest threat, given current discovery statistics, is from the small NEOs. Now these small NEOs are still large enough to reach Earth's surface, with the potential to cause at least as much damage as the Tunguska event in 1908. And to be clear, these are objects that are excluded from the current classification of potentially hazardous objects, simply because they're not big enough. But what our decision model is showing us is that this is the category of greatest concern given our current discovery statistics. And this should therefore be the focus of future decision making by NASA and Congress. And surprisingly, there were only a few parameters that were critical to our model's prescribed decision over the range of values that we considered in this model. One of these was, as you might expect, the value of a statistical life, as I mentioned. So policymakers have either explicitly or implicitly assigned values all across this range we show in this chart here. And this just shows you, as you might expect, the more a policymaker values the statistical life, everything else being equal, the more ambitious of a telescope investment our model prescribes. So this black line highlights the optimal utility maximizing decision across this range of VSLs, ranging from a few 100,000 up to 10 million. We also consider how parameter uncertainty across all of our model parameters affects our model's prescribed investment decision. And to do so, we construct triangular distributions for all of our 58 parameters in the model. And then over 10,000 iterations, we consider how each telescope investment decision fares. So we assume optimal decision making further down the tree, but this just provides us an estimate for the expected utility across 10,000 iterations and gives a better idea of how uncertainty around our many parameters affects the decision. So some contributions of this work, I think we indicated that it's very important to model this decision with very precisely with decision analysis tools, and the important insights we can derive from carefully calibrating those types of models. And a program likely run by NASA to discover and map the smallest NEOs would be the most effective and hopefully allow us to prevent the very large negative outcomes we would see with those larger NEO types. We also provide useful information to support the B612 Foundation mission. And finally, I hope we indicate the value of such an analysis on these types of decisions that are faced by everybody, all countries around the world. And as we show in the paper, there's a clear indication for international cooperation on this issue. So thanks for listening, and if you're interested, please feel free to check out the working paper we have below. Thank you.